Welcome to Mental Math Averages. When we say the word average, we're actually talking about a family of methods to find the middle of a set of values. The problem is that there's a variety of different ways you can define middle. The different methods give us different values for different purposes. In general, when we talk about averages, we're talking about the mean value. But let's take a brief look at the other averages first before we do a deep dive into calculating the mean. The grassy center of a road is called the median because it's in the geographic middle. The median of a set of numbers is in the middle too. We take the median by lining up the numbers and taking the middle value. This is used because sometimes, pretty often, we have a distribution that's heavily weighted to one side or the other. For example, let's look at the salaries of an imaginary tech company. They have 15 people working there, including the two partners who founded the company, who make the most, and an intern and the part-time delivery guy who make the least. Let's look at their hourly earnings. If we take an average by adding them up and dividing by 15, we get $33.87. That's too far to the right to really be considered the middle, as 2/3 of the people working at the company make less than that, and only 4 people make within $10 of this salary. The high salaries at the top end are pulling the average way too much. Let's look at the median salary. To get that, we line up the salary numbers and take the one in the middle, which is $23. This is a better description because 60% of the people working there make within $10 of this value. So medians are used when the distribution is very uneven. The mode tells us what's most popular. If we ask a bunch of people to pick a number between 1 and 10, we'll get a lot more people saying 7 than 8. Unlike median and mean, there can be more than one mode. Something is known as bimodal if there's more than one peak. Modes are mostly used in surveys and elections, or finding out if there's more than one population in a sample. Here's an example of a bimodal distribution from a survey on invention ideas. Note choices 2, done market research, and 3, make rough prototypes, are considerably higher than the other options. The 2 peaks don't have to be next to each other, they can be anywhere in the list. Most of the time when people say the word average, they're talking about the mean value. That's the one where we add all the values together and divide by a number of numbers. The question this answers is, if we rearrange the values so all the numbers are the same, what number would that be? The mean is generally used when values are similar, where the median is better for data sets with large disparities, like salaries. Means are primarily for looking at numbers that are close together, such as different pay periods for a single person. Let's look at some examples and ways to simplify the calculations so it can be done in your head. One example I like to use looks at some stacks of plates. Imagine we have 3 stacks of plates, one with 19 plates, one with 20 plates, and one with 21 plates. If we want to make all the stacks the same size, what do? What we don't do is to put all of the plates in one stack, count them up, divide by 3, and then make each stack that many plates. Instead, we take one plate from the stack of 21 and move it to the stack of 19, so that all the stacks have 20 plates. We can do the same thing with numbers. We can subtract from larger numbers and add to smaller numbers until the values are the same. Let's look at an example. Let's take the mean of these 5 numbers. The 109 is the highest and the 92 is the lowest. So let's move some of that around. How much do we move? A mean has to be somewhere between the highest and lowest value. It's not mathematically possible for it to be less than 92 or greater than 109. It's got to be somewhere in the middle. So let's pick an easy number in that range and work with 100. So let's move 8 points from the 109 to the 92. That gives us this. Then we move 3 to the 97. We can take one of those from the 101 and 2 from the 102. Now we can see that we have 5 points that need to be distributed over 5 values. So the 105 loses 4 points and each of the other values gets 1. Our average is 101. The plate stacking method works best with few numbers and numbers that easily let us see what needs to go where. The last example is pretty much the extreme range for where that can be used. It is, however, the basis of some other methods. Since the mean will be in the middle of the range, we want to look at the variation of the numbers rather than the whole value. So we can subtract off an easy number and work with smaller values, and then add the number back in. Let's look at those numbers again. This time we'll subtract off 100 from each value. Now it's much easier to see what holes need to be filled. We add up what remains and divide by 5 to get 1. Then we add the 100 back in. If we didn't see what points should go where, we could add up the second column and we would still have gotten 5. Now it's your turn. Please pause the video and find the mean value of these numbers. We know the answer will be somewhere around 1,000. The 995 needs 5 points to get to 1,000, which we can take from the 1,005. We then subtract off 1,000, which leaves us 2 sixes, totaling 12. Divide 12 by 4 to get 3, and add the 1,000 back in. Our mean is 1,003. What happens if the plate stacking method doesn't come out evenly? Let's look at our original example, but change the 105 to a 103. We have a 103 and 4 values of 100. Now what? This actually tells us that the average is a fraction between 100 and 101. 3 divided by 5 is 3/5. If we want that in decimal form, we just divide the 3 by 5, as all fractions are basically division. Remember that dividing by 5 is just multiplying by 2 and moving the decimal over one place to the left. So 3/5 equals 0.6. Our answer is 100.6. Back in the addition lesson, we saw some magnetic field data I'd taken. When I take data, I have to average those numbers. So let's look at this as an example of how to average numbers with different units. Let's look at the minutes first. Since there's 60 minutes to a degree, we want to take out 60s. We can do that by moving 8 minutes to the second reading and 6 minutes to the third. So we need to subtract off 14 minutes somewhere. I'll pick 26 since there's no borrowing that way. The 60s change to degrees and give us this. So now we're dividing 35 by 4, which is 8 3/4. Now let's look at the degrees. Because we have two 271s and two 91s, the average is going to be the same whether we add all 4 numbers and divide by 4, or just add one of each and divide by 2. We can use the same trick we did when adding and ignore the ones column because they're the same. 9 plus 27 is 36. 36 divided by 2 is 18. The average of 1 and 1 is 1. So we add that to the ones column and we get the average of 181 degrees, 8.75 minutes. Now it's your turn. Please pause the video and find the average of these minutes in degrees. Did you get an answer? Let's see what it is. The 49 needs 11 points to get to 60. The 52 needs 8 points. That means we need 19 points. We can take that from the 22 and have 3 left over. That gives us a total of 26 minutes. 26 divided by 4 is 6.5. Now for the degrees. We have 2 272s and 2 92s. So we can just average 27 and 9 again and get 18. And add the 2, so our answer is 182 degrees, 6.5 minutes. This works great if the ones column in the degrees has all the same numbers. But what if it doesn't? Let's change one of those numbers to make the ones column not the same and see what happens. We group the minutes and change them to degrees as normal. However, we need the number in the ones column to be the same to be able to ignore them. What do? We could average all 4 numbers, but I'm too lazy for that. Since we're going to be dividing by 4 anyway, let's take one of those degrees out and divide it by 4, which gives us 15 minutes. We hold that off to the side until we're done with everything else. We do the calculations the same way, but at the end we add those 15 minutes back on. So our answer is 181 degrees, 23.75 minutes. If we have to find the mean value of similar sets of numbers, we can do the work once and then look for differences and make an adjustment. We do this by comparing the 2 sets of numbers and finding out what the changes are. In this case, the change is a decrease of 4. 2 from where we went from 105 to 103, and 2 from going from 109 to 107. That 4 is divided by 5 to get 0.8. So we need to decrease the mean by 0.8. Subtracting that off gives us 100.2. The same as if we'd done the work all over again. We can also use the technique of finding differences between the sets so we don't have to do as much math. Consider these two data sets. We've calculated the mean for the first set. So what's the mean for the second? First thing we notice is that the values for the degrees are the same. So our mean value will have the same value for degrees. But how many minutes? Let's look at the differences between set 1 and 2. We see that 25 is up 2 from 23. So we're up 2. The next value is down 1. 2 minus 1 is 1. So now we're only up 1. The third number hasn't changed, but the fourth number is down 3. 1 minus 3 is minus 2. So the total has gone down by 2 minutes. 2 divided by 4 is 1/2. So the average for set 2 will be 1/2 minute lower than for set 1. 8.75 minus 0.5 is 8.25. The average for the second set is 181 degrees, 8.25 minutes. Now it's your turn. Pause the video and find the mean for data set 2. The total difference is minus 4 minutes, so the mean will be 1 minute less, or 181 degrees, 7.75 minutes. Okay, one last set. What do we do if the degrees and minutes both change? We combine the last two methods. Here I've added an extra degree to set 2. We pull that degree out and divide by 4 like we did previously. Then we ignore it for a bit. We find the differences in minute readings and subtract like we did before, getting 8.25. At this point, we add the 15 minutes back in to get 23.25. So the mean from set 2 is 181 degrees, 23.25 minutes. Note, the method of finding the differences is easiest if the numbers are similar, like what happens if you're taking multiple measurements of the same thing. In addition, you have to be very certain that your first set of averages is correct, as if they aren't, everything else will be wrong as well. Next up, my favorite, percents and the 10% method.